Hello, everyone. Welcome to Becoming a ROS Developer here at The Construct. My name is Rodrigo. And today we have one of our students who's going to show us what he did for his ROS Basics project. And he learned it in both C++ and Python. He's going to show us the project he did. His name is Girish. Hi, how are you, Girish?
Hi, Rodrigo. How are you?
I am good, thank you. So yeah, whenever you're ready, you can start sharing your screen and show us your project that you did in the real robot and just explain us a little bit about it.
All right, sounds good. So let me go ahead and start sharing my screen.
All right.
All right. Okay. All right.
Okay, I can see
So
your
what I
screen.
should be. All right. So now I'm going to start my C++ version of my robot, and it's going to be ROS launch, ROS CPP basics C++ version of my main.launch.
And while it's doing its thing, can you just explain generally what the robot is doing?
So the robot does three things. It does it finds the wall and it starts doing a wall follower algorithm. And
Uh-huh.
then while it's doing a wall follower algorithm, it calculates it gets the odometry values and calculates the distance travel throughout the lap that it does when from
Okay.
the start to end.
All
And
right. So
yeah,
right
now
now
as you
it's
can
looking
see,
for the wall, right?
yes, and now it's moving towards the wall since it has found a valid wall.
Okay. We see that we have some
Yep.
spectators there in the real robot lab checking
Yeah.
your algorithm, so that's nice.
Now the robot has stopped in front of the wall and it's aligning itself to the wall, which is the third part of the find wall method, wherein it aligns itself so that the wall faces on is on its right.
Okay, and that way you can start doing a loop around it.
Now the find wall is complete, and now it's positioning parallel to the wall to start the wall follower process. So you just want to make note of the point it starts. So because my robot starts and stops the same point, and
Uh-huh.
neither the robot nor I know where it starts, so it's not hard coded.
Oh, that's
So
nice. That's
right now it has started from the pedestrian crossing zone somewhere around that area. Now
so it
it's
should stop
moving.
around that area.
Yeah, it should stop somewhere around that area, like more or less closer to that area.
Okay, great. So yeah, whenever you want, we see that it's doing its thing. Let's see if it completes the
Hmm.
loop. So you can start. So you divided the project in three parts, right? In a service
True,
server, in a main program, and
true.
an action server. Uh,
Hmm.
can you tell
I
us?
do have a presentation.
Oh, perfect, perfect. Then we'll check it out.
So, do you want me to bring that up now, or we want to wait for the robot to complete?
It's up to you. If you trust your robot to stop, we can
Uh,
we can get started. But
I'll just I'll just have one of my I'll just have my PowerPoint coming up in half of the screen. So
great.
let's CPP. All right, let me close this one.
Oh yeah,
All
look,
right,
this
so
looks nice.
slideshow. Second first slide. Okay, that goes way into the screen. All right, so slideshow. So settings in a window. Okay. All right, so start slideshow. First slide. All right,
Oh,
so
this
here
is
we
amazing.
have this is my course project. So introduction, the problem scenario is that we need to program a robot using ROS, which would perform wall following algorithm with the ability to automatically detect a nearby wall and orient itself towards it, navigate itself within the area while performing wall following. And before we continue, let's see if the robot finishes in the landmark zone. Yeah, it stopped right there, so I'm going to minimize this one. It stopped right there, and the goal is complete. Seems to be complete. All right, it is not complete.
Well, but we see the total distance, and we saw that it
Yes.
stopped. Maybe it got lost in the output.
It needs to track one at the end of the landmark trail you can see on the screen, like the array,
Mm-hmm.
but it is not printing the landmark array. And I'm not sure why. Probably we should just restart it.
Yeah, try it again and explain in the meantime uh, what it was.
Let me just
Maybe
let
we
me
can
just
understand.
reposition the robot. Alright. Alright, so let me just restart the code. Hopefully this time it performs well. So let me just go back to the presentation.
Yes, please.
So yeah, as I said, it automatically detects a nearby wall and orients towards it, navigates itself within the area performing wall following algorithm, and it records the odometry all through the lap or every lap while it makes the wall following movement in the arena, and it avoids collision with walls or obstacles along its path.
Mm-hmm.
And then the parts of the project are three of them: topics, services, and actions. The topics performs the wall following algorithm. It uses publishers and subscribers available in ROS to communicate with the sensors and actuators to navigate the robot within the region. And then the services uses a server and a client to identify a nearby wall with specified methods for the robot to start its wall following algorithm. And then the action uses two parts again as the server and the client, which record the pose and orientation of the robot through the course of its path to make uh, to record the odometry.
Mm-hmm.
And there are two custom service messages used in this ROS project. One is a find wall service, which has an empty request and a boolean value to as a response for if whether the wall is found. And then for the record autumn action, we have three parts of the message. The goal message is blank. The result is a set of 0.32 values, which is named as list of odoms. And for the feedback, we are just sending current total, which is just the distance covered by the robot uh, instantaneously, like till this point during while it's doing the lap. So the find wall service has four parts. The first part is head towards the shortest ray, and it uses some math. So basically, it performs a 360-degree scan, and then it decimates the value from the ranges to about two decimal places to allocate into separate small groups. And then the shortest ray is calculated as the average of the smallest ray that has the most or the maximum frequency of occurrence. And then it rotates towards the smallest ray, which was calculated before, like in the previous step, and then aligns itself to the smallest ray range. And then it loops over until this is matched for 15 seconds.
And this allows you to differentiate between the wall and say an obstacle.
Yes, so that is where we use this fine tuning method. So this method gives you this method differentiates between the obstacle and the wall. So this method gives you the result pointing towards the wall and not an obstacle.
Mm-hmm.
And then to verify if we are pointing towards the wall, we perform a scan for valid wall function. So this again starts by performing a 360-degree scan, and then it gets a frontal 120 degrees of rays. In other words, 240 rays, because the laser scan is capable of doing 720 value sweep, which means for 360 degrees it's 720, which means you have 2 rays per degree. So you have
Mm-hmm.
240 rays to choose from, and then you choose the direction by rotating about you choose the direction to rotate by comparing the shortest ray range on either side of the front ray. The front ray is 360 exactly, the value is 360. So you compare 120 degrees of rays on the left and 120 degrees of rays on the right, and then you choose the side which has a lesser range of either side, and then you calculate the mean and standard deviation while keeping track of the previous range and standard deviation values. And then you loop over until a condition is met. The condition is that when the mean is greater than standard deviation, that is, the standard deviation is less than mean, and then the previous standard deviation is less than the current standard deviation, and the previous range is less than the current frontal range, your loop is done. And then you just rotate a little bit to make sure that the previous rotation change is reversed for a little bit, and then you stop. This is your valid front wall. And
Mm-hmm.
to explain more about this front wall, on your screens, you see four types of wall facing the robot facing wall. So the first one on the top left is the robot facing the obstacle, facing the corner of the obstacle. On the second one, which is on the top right, the robot is facing the obstacle but on the flat side. The third one is the robot is facing the obstacle, which is on the bottom left. The bottom left is robot facing the obstacles, like multiple obstacles in front of it. And then the fourth one is actually the robot facing the wall. So it faces the wall like plain blank line in front of it. So when you look into the mathematics of this part, if you can remember, the top left was the robot facing the corner of an obstacle. So the 360 degrees is the robot facing the corner of the obstacle. So when it faces the corner of the obstacle, the frontal 120 degrees of the rays would yield a graph like this on a 2D Cartesian plane. And then
Mm.
when you get the frontal 120 degrees, and then you just take the frontal 120 degrees and map it out, you'll see that there are some statistics that will get you some result. So in my graph, you see the red line is the maximum of the value, the cyan line on the bottom is the lowest value of the range, the green line is the mean. So just to sound mean green, it is green for mean, and then
Mhm.
yellow is for standard deviation.
Okay.
And if you look if you understand this graph, if you have the robot facing the edge, you have this kind of reading. When it faces the side of the object, like obstacle, it has this kind of reading. And then when it faces multiple obstacles, it has this kind of reading. And then when it faces the wall, it has this sort of reading. So the point to note here is that when it does not face a wall, the standard deviation is way above the minimum of all the values. So
Mm-hmm.
the yellow standard deviation line, it is way above all the minimum lines. But when it faces the wall, the standard deviation is well below the minimum of the values. So that is the criteria which I use to find a wall and validate it as a wall.
That's amazing.
So
This is really, really
so
impressive. And how did you know to approach it this way? Have you done other work?
because Yeah, I've seen some other filtering methods and other stuff, but those tend to take a long time, and we need a short answer that is instantaneous.
Mm-hmm.
And I used to work as a audio engineer, so I'm good with statistical analysis of data points and data streams. So I just went for a toss and analyzed what would happen if I
Right, with the
do this,
standard deviation.
and this one seems to give me good results.
Awesome.
So yeah, and if you plot the rays on a polar map, you get the actual diagram, actual arena itself. But if you plot them in a Cartesian plane, you get this some sort of uh, a line which is neither a mountainous looking line or some sort of a necklace looking line.
Mm-hmm.
So this is just a difference. So if you convert it to a Cartesian plane, it can help you interpret it better.
Right.
But the polar plane will help you understand a robot's orientation better. And the next part of the find wall is to move towards the wall, which is just keep moving towards the wall until the frontal range is zero point 0.3, and then align yourself with the wall. When you're facing the wall, take the front right value, which is 270, which is the ray number 270, and then compare with the frontal ray range and the 270th ray range, and when they coincide, you have found the wall on the right side of the robot. So once this is done, you consider that the service is complete.
Mm-hmm.
So the pros and cons of this method is that it finds a valid wall correctly. By valid wall, I mean the output from the second of the method, which is the scan for valid wall after the standard deviation processes. But the cons of this method is that it's tedious or time consuming. The algorithm does actually have a dead zone where it does not complete. So it goes into
Where's
a
that?
while loop or a spinning. So these are the dead zones of this algorithm. So
Ah.
if the robot is within the red zones, it'll never converge, and it'll keep on finding the wall forever and
It'll
ever.
keep on spinning.
Yes.
So it won't find a spot where the standard deviation is, you said below?
Yes.
Or what was it?
Yeah. It's like way less than the minimum
Uh-huh.
uh, because on the corners it's actually a negative corner, so it's facing away from you. And the dead zone in the middle is actually the place where on the left and right of the robot the values are almost the same.
Yeah,
So the robot cannot decide which direction to take and keeps spinning around always, like
right.
keeps spinning off forever.
That's really interesting.
And then here's the record ODOM action. So you initialize the server and goal callback, and then you initialize the landmark zone, and then you initialize the odometry subscriber and its callback. So the goal callback goes as follows. So you clear the feedback and result variables. You initialize the landmark zone while the robot is stopped, and then you check for goal preemption, which is a necessary condition to make sure that the goal is not terminated on the other side.
Mm-hmm.
And while the goal is happening, you get the odometry for a pose of for x and y, and then calculate distance between the previous odometry value and the current odometry value to get the distance using the uh, Cartesian distance method. So then you update the feedback value and then loop over the previous three steps until the robot stops in the landmark zone. And once the robot is stopped, you send the result to the main code, and then you mark the robot as stopped, and then the lap is complete.
And how do you initialize that landmark zone? What does that mean?
So I actually have the robot stop once a robot is positioned towards the wall.
Along the
It
wall, yeah.
stops for like, yeah, closer to the wall. Yeah, next to the wall. It actually stops for about a few seconds, which is like around 2.5 seconds. And that time I actually send the goal to the action server, and then there's a small snippet in the of code before the goal callback starts, wherein when the robot is stopped, that is I'm getting odometry there, so I'm using the instantaneous velocity values to
Uh-huh.
check if the robot is moving, and if they are zero, the robot is actually stopped.
Yeah.
And when the robot is stopped, it initializes the landmark zone once, and then it just keeps waiting until the robot starts to move. And once the robot starts to move, it goes into the point of odometry pose and XY calculation and stuff.
Okay, I see.
So when the robot stops, the goal callback also stops because it has entered the landmark zone, and then the result is given back to the main code.
Okay.
Both the main program and the action code has a trail of landmark, which is an array of true or false values. So just to keep track of the last 15 seconds of robot's movement. So once it leaves the landmark, it initializes the goal, and once it enters the landmark, it finalizes the goal. And then we have the pros and cons of this method too. So it records the odometry from start to finish without any problems. But the cons is that this specific method cannot be tested with AX client, which is a part of the ROS debugging
Mm-hmm.
uh, uh, framework. So although I have a similar callback called test callback with which you can use to use with AX client to check your results, but this specific record ORM method that I am using in my code right now cannot be tested with AX client. That is the only con of this
Right. You
record
could
ORM
you could
method.
use a ROS bag, maybe.
Yeah.
Okay, all right, okay.
And then finally to the topics, which is the wall follower algorithm itself. So you initialize the publisher for command velocity to move the robot, and then a laser scan subscriber to get the laser scan ranges. And the wall follower algorithm is very simple. You go straight until the frontal reading is greater than zero point 0.5, and while it is greater than zero point 0.5, the robot goes away from the wall if the right side range value is it goes away from the wall if the right side value is less than zero point 0.2. That should be the opposite over here. So man, this actually should come on top.
Okay.
So it goes it goes away from the wall if the right side value is less than zero point 0.2, and it goes towards the
Towards the
wall
wall.
if if the right side value is above zero point 0.3 meters.
So it stays
And
between
then
point 0.2 and point 0.3.
yes, and then it makes it just makes a smooth turn to the left if the frontal reading is less than 0.5 meters, which wherein it has just reached an obstacle or a wall ahead.
Okay. So
And then the
I'm sorry.
yeah.
Keep going.
So the pros and cons of this wall follower process is that it properly utilizes the scan readings to follow the wall and then avoid sharp turns in the corner. The only problem with this method is that due to the continuous scan and move method that I'm using, the robot follows a non-linear or a curvy path instead of a linear path. So as the typical robot wall follower method, which uses like robot moving straight parallel towards the wall, this method would actually not move the robot parallel towards the wall, but it moves in a faint snake-like
Like
manner
a
where it
snake.
takes a
Yeah.
curved path. Yeah.
I mean, but a simple way of fixing this, or not fixing it, just reducing it, is doing it between point 0.2 and 0.21. See, maybe that does something to it. Obviously, that would make it seem more like a line, but I wouldn't
True.
consider that a con based on this application. But yeah.
Hmm. And this is just the all parts combined logic. So initialize all the publishers, subscribers, clients, and actions, services and actions, and then find a valid wall and orient the robot next to it and start the wall follower algorithm. And then this is the main part. So follow wall action process. This includes a communication with the action server as a client. So you adjust the position parallel to the wall, you initialize the landmark zone on the main code, send the goal to the action server, loop over until the wall follow algorithm is complete or reaches the stop zone. And then you break the loop once the robot completes a valid lap. And then you just write the record odometry action result into a log file, and then you get ready for the next lap.
Great.
So debugging in ROS is done with four methods. So you have the RQT console, and then you have the RQT plot, and then RQT graph, and then RViz. So
Which one did
let
you
me just
use the
minimize and show
most?
you the.
Oh,
So yeah, it's
yeah,
supposed to
because
be an
it's
RQT.
it was 25, so the
Mhm.
your reservation was
All right,
done, but
so I
you can
think
launch the rush check
I
then.
do have a video of what I've done, so I can probably
Yeah, yeah, let's see it.
the show you that. But before that, let us finish off with this one.
Mm-hmm.
So these four. So videos. You have the RQT console first. With this one, you can actually separate out the debug messages from the main messages. So, so on the screens, you can see the debug messages showing up in green. And then now I'm starting the ROS console or the RQT console.
Mm-hmm.
Okay, so yeah, once the console starts, you can just check uh, the messages just by disabling the messages you want and
Mm-hmm.
you don't want. So now you're seeing the debug messages, now nothing, now it's just info messages. And then once you click on info, everything goes away. There's no warning, error, or fatal messages at the right now.
Do you use this often?
Yes, I do because if you are printing messages on your screen, debugging with messages alone takes it is very difficult because you have a lot of message, but with RTD console it is actually efficient because you're able to separate out what info you need and what info you don't want
Exactly. Yeah.
instead of just printing a bunch of uh, strings which you don't want to look at or
Yeah. Straining your eyes trying to find the
true
things you
true.
need.
So
Yeah.
so the next thing is RQT plot. So in this, there's just another framework within ROS which gives you an idea of how to trace values. So in this graph, I'm actually showing you how to trace the scan ranges. So the blue line is actually the frontal scan range, and the red line is the scan range on its right. So you can see that when the robot moves, it actually increases and decreases
Mm-hmm.
based on the measurement it gets.
Yeah, this one's great too. I actually, I recommend you check out this one called Plot Juggler. It's called. I don't know if
Mm-hmm.
you've heard of it. You can
No, I
download it
haven't.
for ROS, and you can add
Mm-hmm.
any topic, and it's like RQT plot but on steroids. You should check it out whenever you have
Gotcha.
time. Yeah.
Sure, sure. I've made note of it. All right, let's close this one and then check the RGD graph. So this gives you an idea of what is communicating with what within your ROS programs. So this is your active list of communications happening within the robot. And then once you change the top filter to nodes and topics all, you get this map which gives you which nodes communicate with what other nodes, and then how the communication takes place, and how gazebo is linked with ROS core
Mm-hmm.
for simulation purposes, if you're on simulation. And then finally we have the RViz, which helps you debug your robot in real time. Not exactly what while using ROS. So with this simulation, we can see what the laser scan range is measuring, the measurement, uh, the device, the lidar is measuring,
Mm-hmm.
and then with the proper things enabled, like laser scan on the displays panel, you can see what the robot is actually seeing uh, with the with the laser scan. So once you go in, you can also see the image of the robot, landscape, like overview of it if you have a camera, and
Mm-hmm.
then you can also see what the robot is perceiving by using the camera in front of the robot, which is this one. So while the robot moves, you'll be able to see what the robot sees in front of it. But this project does not use camera, so just showing you the images taken by the camera. So this is the laser scan, what you see, and
Yeah.
it shows you the arena as is, and the obstacles. And you don't see a complete box, because wherever the ray passes through an obstacle, the ray is stopped over there, so the box is not complete. So yeah, that's that's what all you can do with. More than this, you can do with RWish.
Great display on the debugging tools because I think they're very, very important, especially to understand ROS better and to find errors quicker. I think it's
True,
important.
true.
So great way of showing everything you did for debugging.
You can also use the odometry values, but because this page turned yellow, I did not continue using that.
That's the actually
So
that's the I think it's the standard deviation or something of the
mhm.
odometry. So when you turn it on, there's two in Y and X.
You mean the covariance?
Covariance, yes, yes. I don't know
Okay.
why it's so big, but those where they are. They grow and shrink depending on things. But yeah, that's the yellow thing.
All right. So that is all with the RWish tool,
Great.
and
Now
then
your case,
finally,
let me tell you.
yeah.
Are you? Oh, are you done or?
Not yet. So the
Okay, okay.
last part
Sorry.
of the project is that when the robot completes the path, it records all the odometry in a file, and then it displays what it has. It displays the path in a graph, which I'm using a Python code to graph it using matplotlib. So the file just looks like this. So it's just a file with all the values. So ODOM results log. So once you open this, you'll find there's a bunch of x, y, z values. These are not actually, these are actually the x, y, and theta z, which is the
Yeah, I was gonna
degrees
say,
of
wow, that moved
orientation.
up and down a lot.
So, and then in the last part, you have a separator line which shows you the distance, the average speed, and the time taken. So here you can see it's 5.9,
Oh,
0.
nice.
0.07, and 84. So that gets translated into this graph, which is 5. Uh, Not this one. So it's translated into this graph. Yeah, translated into this graph into the distance, speed, and odometry
Right.
values. I mean, distance, speed, and time values. And yeah, there are some explanations, a little more explanation. So as to why the lap will start and not stop at the same place. So due to the landmark tolerance limitation, the robot makes the initial point a start, and the landmark start point is landmark completion for a lap. So since the probability of the robot starting and stopping at the same point is not a sure event in terms of probability, the landmark zone is specified. So the landmark zone is a small square region, as you saw in the picture, which is this one, this square region, calculated
Mm-hmm.
from the point of initialization of the robot. So so when the robot finishes a lap, it stops anywhere within this square and it's considered to have completed this lap. And thus there is a small gap between the start and the stop points, which you can see in this image. Like they are not aligning exactly on the same spot, but there is a they both are well within the landmark zone itself.
Mm-hmm.
So that is why we have the gap between the start and the stop point.
And how did you decide the size of this landmark zone?
So that is actually a tricky explanation. So what happens is that if you choose a smaller x, x you can see is the horizontal line and the y is the vertical line. So
Uh-huh.
if you choose a smaller x, it will not stop. The robot will not stop if the robot is started from the left side. So the x gets reduced, and then when the robot comes over like this, and if it starts from here and the robot comes in like this, it will not merge on the landmark zone. And similarly for y, if the
Uh.
y is too small, if the robot goes over this point, if the robot starts over here, let's say, and then if the robot goes over like this,
Mm-hmm.
since the landmark zone is smaller in y axis, it will not stop and just continue to move until it comes into the landmark zone. So thus, a valid tolerance limit was a square box, which would account for the distance between the robot or what it might actually go through.
Right. So a square big enough that it recognizes the when it returns, but not too big, so it just defeats the purpose of the landmark zone, right?
Precisely.
Okay. Okay.
And
Okay.
it should
Nice.
also make sure that the landmark box does not fall into the place of the obstacles.
Yeah, of course.
So the robot doesn't go in front of an obstacle and then hit itself and then stop over there, assuming it's complete a lap.
Yeah.
And that, I guess, would be all of it. Well, yeah, and then we have the areas to improve in this project. So the wall follower algorithm itself, it must be more linear and less curved. The service must be lesser time consuming and a sure shot way to find a wall. The action must have a better way to perceive a start point and a landmark. And there should be a use of IMU for better positioning and pose estimation, and for more precise distance calculation and speed calculations, and probably more comments on the code for easier understanding.
That's an eternal problem
And
for everyone, so don't worry.
that would be all my presentation.
Well, really, really well done, Girish. Let me. Well, your case is a little uh, specific because you did the C++ project as well as the Python project.
Hmm.
Can you tell us the main differences besides the fact that C++ is just inherently harder to pick up if you're a beginner? Can you tell us the main differences between one project and the other
Sure.
that you
The
found?
first difference is that the Python is actually way more easier when it comes to classing and subclasses utilization as opposed to C++.
Mm-hmm.
The only place you have the only place that is tricky for any beginner for C++ with Python is the actions, because it is pretty hard to understand uh, the actions part, especially the server and the client. So this is the server, and then you have the client right here. Open folder, cpp, open. Okay, so it does not load. So okay, there it is. So resource. client. So this is where the people usually find it hard. So when you're using classes in C++, the sendGoal method actually calls a reference to the callback method, and then the ROS documentation itself is not so easy to understand. And this is where I spent about like 4 to 6 hours, I believe, to understand how this is going on. And this is the only place where it is pretty difficult. And it is just a place where actions and classing is a difficult part for any beginner to understand
Mm-hmm.
ROS coding with C++. Otherwise, ROS with Python is a good place to start to understand how processes and procedures take place, and then converting it to a C++ would be a method to do deployable codes wherein you test your robot functionality with Python and then transcode it like I did to C++ so that you can make the robot faster and more efficient
Mm.
and make it more deployable.
Right. Right. Right.
But otherwise, there is no difficulty in C++. Although you need to know how to code in C++, the very basics, but otherwise there isn't anything different, I believe.
All right. Well, other than that, I think I'm done. Do
I
you
do have a
mind?
video to I do have a video to show you. So
Let's see it. Yeah.
I have a C++ completing over here.
And this we saw in the beginning. Just a reminder to everyone. Um, in the beginning of the presentation, you can go back and see it in real time.
So this is moving towards the wall right now, and then after some time it positions itself. I'm just going to quickly go through this video. So it keeps going, and then it completes right there from the place it started. So it's going to
Mm-hmm.
complete right now, and then once it reaches the lab, it has finished.
And it
So
spits
I'm
out.
going to pause right here. So it spits out all the values, like the result, and then you can see that the odometry results are also out. So it's the total distance covered in the lab is like 5.8. The time taken is 142 seconds, and the speed is like 0.04 meters per second. And the next few seconds will show you the tracing or the outline of the.
Yeah, I saw a nice graph.
So I call the Python code here to print to generate the image for the odometry. And yes, that is the image.
And you
So
use the log that you showed us earlier, and you put it into that Python
yes,
to spit
I'm
this out.
just reading the Python file, as in like the log file in Python, and
Yeah.
then just plotting the graph of all the values that I got from the result. And then there you can see that the box is there, the landmark zone, and then you can also find that the stop zone is not exactly on the close to the initial point, but it's well within the landmark zone. So
All
that is
right.
where the
Yeah.
lab completes. And then you can also find that the distance is 5.86. I wish I could zoom in, but I don't think I can. So yeah, that is 5.86, and
We
the
can
speed is
kind of see
0.04
5
as we
point
saw earlier.
something. Yeah.
And then the time is 142, which we saw earlier, which is like right here. So right there. All right. So yeah, that's pretty much it.
All right. Well, that was really, really
Uh,
nice. Really complete presentation, Girish. Do you mind stopping your screen share? That's the
just a
one.
minute.
That's
So
the what
this
you were
is
trying to show right there.
yeah, this is the one I'm trying to show you.
Yeah.
So this is 5.8, 142, and 0.04, and then that is the one you have over here, which is
It's just
5.8, 0.04, and then 142.
great.
So that is the entire trace of the odometry,
Really nice use of
and
the
that
logs
completes.
too. It's the first
Thank
time
you,
I see that
and
in this project, so really nice. Um,
and that completes my project.
All right, Girish. So congratulations. Do you mind stopping sharing your screen so we can see each other
Sure.
here?
Stop sharing. I probably have to reload my video.
All right. So I
All
think
right, there it is.
there we go. So congratulations, Girish. That was a really
Thank you.
complete
Thank
project, especially since you completed both the C++ and the Python projects. I
you.
loved I loved how you did the wall detection. It's the first time I see that thing. You said one of the cons was that it was really time consuming. Well,
Mm-hmm.
yes, because you did it so robust, and I think yes, you could probably find really quick filters that you can find online that does pretty much the same thing, but that is really impressive because it came from you, and that's why I asked, like, how did you know how to do this with the standard deviations and the means? It's just shows that knowledge that you have from other work you've done can
Previous
translate
experience.
here, and it's really powerful. So I that was my favorite part, and yeah, so that
It was
scan
just a
for
hit and a
valid
miss.
wall. I'm sorry.
It was just a hit and a miss, and it worked out well.
Yeah, it worked out well. Yes, and and the debugging tools, it shows that you've taken your time to really understand what's going on with the ROS
I did also
system.
use a ROS bag. I did also use a ROS bag, but I've not showed it over here.
Oh, I see. Yeah, but yeah, that's it's just the last one pretty much. But
Hmm.
I thought everything was really well explained. The logic was very clear, and that's how you were able to translate. Like you said, you started in Python and then moved on to C++. And I think the main reason is because you had the logic like really
Hmm.
well figured out, and yeah. Other than that, congratulations again. It was a perfect project, and congratulations.
Thank you. Just another note. Python helps you complete stuff, while C++ helps you deploy stuff. So it is just better to go Python first and then go C++
Yeah,
first.
there you go. Because you might want to change things, and you'll spend a lot of
Hmm.
time in C++ if you do it all there. So yeah, that's a good
True.
suggestion.
You just wanna see a thing doing its thing first, and
Right,
not spend time debugging your code before it actually does something.
right. You want to make it work, and then make it work very nicely. Yeah, I
Exactly.
understand. I agree.
Exactly.
Um, but anyways, Girish, thank you so much, and to everyone else watching, this is what you can do when you take our courses, and then expose the knowledge that you've acquired, and like Girish here, you can do things that no one else has really done in this little simple project. You can expand it so much, and you could just expand your learning like that. So this could be you guys, and so if you want, take our courses and come here and present it with us, and yeah, we'll see you guys next time for the next one. Girish, thank you very very much again.
Yes, the construct is a very good place for us beginners and starters. So please do join in there.
Well, thank
Unlike
you.
compared to other places like Coursera and EDX, ROS does offer a lot of courses to get you well developed in ROS.
Right.
So the construct actually offers a lot of courses to get yourself developed in ROS. So don't miss it.
That's what we love to hear. You heard it here from Girish. Join the construct and learn some robotics, guys. I'm Rodrigo again. I'll see you next time for our next video. Bye bye, you
See you
guys.
all. Bye.
All right. Cool.